start this lecture with a thought process. Asking a question is not the end of a thing. One can assume it to be a humble beginning. If explored honestly without bothering, one can definitely have a happy ending. So, in the last lecture we have learnt how to evaluate the burning velocity by making a lot of assumptions, and also we will have to evaluate the properties properly. Otherwise, you will land in getting some number which is having not much meaning, right. But today we will be trying to look at and the flame thickness and also try to relate that to the burning velocity. So, later on in this lecture we will be looking at how to evaluate the burning velocity experimentally, right. What are the methods being used generally for evaluating the burning velocity. So, flame thickness if you look at is basically a ratio of the maximum temperature difference to the temperature difference at the inflection point. This basically inflection point you might be knowing that where the slope will be changing, right, of the temperature profile. For example, if you look at this here, this is the temperature profile, and we of course will be approximating as a linear profile for our computation. In actual situation there will be a curvature here kind of things, and the inflection point will be somewhere here where the slope is changing from positive to the negative kind of things. So, that we will define as the delta L is the flame thickness. This is your flame thickness. I will take a tangent and then do that. So, that is nothing but Tf minus Tu divided by T at the ignition we can take approximately, right, and T ignition can be approximated as 0.75 Tf plus 0.25 Tu. So, temperature gradient at the flame surface will be, we know that T ignition is nothing but your 3 by 4 m dot double dash Cp divided by Kg Tf minus Tu. This already we have seen, right. So, if I say this is equation 1, what I will do, I will basically substitute these values like flame thickness. So, flame thickness I can write down this as delta L Tf minus Tu divided by 3 by 4 m dot Cp by Kg Tf minus Tu. So, this you can cancel it out, and you can write down basically this is 4 by 3, right, Kg by Cp, and m dot double dash is nothing but your rho u SL, right, and this I can consider this as alpha. This is nothing but your 4 by 3 alpha divided by SL. So, I can write down this S equal to 4 by 3 alpha by SL, and this is alpha is basically thermal diffusivity, Kg, and this is evaluated as average temperature, rho u evaluated at Tu, right, and I can write down at evaluated as Tu, and Cp is evaluated as. So, what it indicates? It indicates that flame thickness will be inversely proportional to SL, burning velocity. The burning velocity will be higher, the flame will be thinner, and burning velocity will be lower, the flame thickness will be thicker, right. And this flame thickness will be order of mm kind of things. and if equivalence ratio is 1 for a hydrocarbon air flame, right, the burning velocity will be what maximum you can get. But when you will go for the lean side and the reach side, you will find the burning velocity is decreasing. That means flame become thicker towards the either the rich mixture or the rich mixture, lean mixture or the rich mixtures, right. So, these kind of things will be helpful because the flame thickness is basically depend on the burning velocities, right. We will be looking at little later on that the other things like your quenching diameter and the ignition energy all can be related to the burning velocities. So, therefore, the burning velocity is very important parameter in case of laminar premix flame. So, if you look at if it is delta will be decreasing when SL delta L basically will decreases when SL increases and vice versa, because it is inversely proportional to the because the flame thickness is inversely proportional to the burning velocity. Now, we will be looking at how to measure the laminar burning velocity. There are various methods available in the open literature, however, we will be looking at some of them. And these measurement methods for burning velocity can be broadly divided into two categories. One is the propagation method, or when the flame will be moving at certain velocities. Other is the stationary method, like where the flame has to stabilize and then you measure the burning velocity. And in the propagation method, the flame front will be moving with respect to laboratory coordinate system, which is basically fixed coordinate system. And there are three of them which we will be discussing. One is tube method, the combustion bomb method, and the soap bubble method, right. And stationary method, there will be also two of them, like Bunsen burner and the flat flame burner, right. There will be several other things also. And in this case also flame front is fixed to the with respect to laboratory flame. So, but question arises, all this in the case of propagation method and also in the stationary method, you will have to identify the flame surface, right. For that three methods are being used. One is luminous photography, which we directly take, and then because of color you will get a shape of the flame photograph. Other is shadowgraph, where you will be using some technique shadowgraph, which you might have used in your fluid mechanics, and Schlieren photography. And if you look at this, if I take this flame thickness, Schlieren zone will be in this region in the initial with respect to basically, if you consider this is Tu and this is Tf, and shadowgraph in between, right, and whereas the luminous zone in the higher temperature zone where the luminous photograph will be coming. So, luminous part occurs at the burnt side, as I told, and flame speed with respect to unburnt gas is required. So, therefore, some correction has to be done, because always we define the burning velocity with respect to the unburnt mixture, because this is your unburnt mixture, right, and this is burnt side. And shadowgraph correspond to second derivative of the density, because if you change temperature is changing, so also the density will be changing. So, closer to the inflection point, like somewhere here, right. So, where the slope will be changing. And Schlieren captures the maximum first density of the gradient and closer to the unburnt mixture. Therefore, it is more preferred, because you need not to do any correction, it is just basically with respect to the unburnt mixture, and which is according to the definition of the burning laminar burning velocity. But however, for the optical systems and other things are very cumbersome. In case of Selenium, people generally go for the luminous kind of things, because it is easier to do that, and also it captures the flame, because flame will be not in this region, because no reaction will be taken. This is coming under preheat zone, Selenium 1, right. So, therefore, that is a confusion, but generally people go for luminous images more, and some people go for Selenium also. Let us look at a tube method. What you can do? Tube, it is a horizontal tube which you fill with the fuel oxidizer mixture to start with, and then of course, there is a some kind of a nozzle, you can say, through which the mixture can move when the flame front is moving, right. So, when you ignite, there will be a kernel, right, small one will be coming, then it will be growing, it will be moving in the direction. After that, it takes some certain shapes, right, and this need not to be one dimensional, basically it is a two dimensional. Why? Because of there will be some buoyancy effect, as a result the flame takes a different shape. And this was basically developed by Maillard and Lee Chatelier in 1883, and they have also given the thermal theory, which we have already discussed that, but it is little modified version than the Maillard and Lee Chatelier. Later on it was modified, that we have discussed for finding out expression for laminar burning velocity. So, what you will have to do, basically combustible mixture is filled in the tube, and on ignition at one end, flame propagates through the tube, and keep in mind that the diameter, this if you look at, this is the diameter, this diameter should be greater than the quenching diameter. You might be asking a question, what do you mean by quenching? As the name indicates that if the diameter is small, then heat losses will be very high. If heat losses is higher than the heat release, then flame will be quenched, it will not propagate. So, that diameter, inner diameter should be greater than quenching diameter. Generally, what happen, around 50 mm diameter is being used, because if it will be too big, then what will happen, buoyancy effect will be much higher, because even though horizontally some of the gases will be having higher lower density, then it will go up and the flame will be distorted. So, that also has to be taken care. And the flame is planar at the beginning and curved towards downstream due to the buoyancy effect, as I have already discussed. So, if the diameter is larger, then the natural convection disturbs the planar flame front due to difference in densities of the mixture, right. And of course, the friction at the tube will also reason for something parabolic shape, that is another reason, because there will be some heat losses and also the friction between both the actually wall of the tubes. So, that will make the shape of the flame to be parabolic. The burning velocity you can write down, basically SL is equal to Vf minus Vg, right. Vf is this one, flame front movement, and Vg will be some gas will be going out, because of the flame front there will be some expansion of gas. Expansion will be trying to push some gas out, and this is Vf is the flame front velocity, and Vg is the unburned gas velocity through this, which will be coming. At is the cross sectional area of tube. So, if you look at this is your AT, and AF is the flame surface area. If you look at this area, will be flame surface area, right. and this area which you will be getting from the flame photograph, right. Basically that you will be measuring rest and also Vf you can measure by locating the flame and then taking with respect to time, then you can find out what is the L and then how much it has moved. So, Vf you can find out, this is from the experiment you will have to find out this, and this is already known tube, and Vg you will be also estimating like how much gas is going out, that is little difficult to evaluate, right. What you can do, you can also put some balloon and see that how much it is going out. This measurement of Vg is not that easy, and sometimes you can neglect that also, and then approximately you can measure. So, therefore, if you know this Vf and Vg At of course is known already because you have taken the proper tube. So, you can estimate the burning velocity by this method, laminar burning velocity of flame. And this is not a very accurate method because there is a lot of involvement, but it is the simplest method one can think of. So, therefore, it is being used to estimate the laminar burning velocity. And this is as I told, like this is basically there will be heat losses from the wall, right. There will be some heat losses, it is some finite values, right. And also the buoyancy effect will be there, which is not taken care in this formula or expression. So, therefore, one has to be very careful about this measurement system. So, how to overcome this problem, but you can use a vertical tube instead of that, right. When you use the vertical tube, then particularly the buoyancy effect will not be that, it will not disturb the flame, right. And it can be flame can propagate upward and flame can propagate downwards, right. So, that also if it is flame is propagating downward, then buoyancy effect will be coming, and when you propagate you need not to really worry because hot gas is already there. So, that has to be taken care, and then the combustion bump which is being used, like you can have a chamber combustion bump where you can mix this fuel air and then ignite at the center, and in this generally the flame kernel will be coming, right, if it is ignition, and then flame front will be moving. Keep in mind that if the chamber is large, again buoyancy effect will be coming into picture, right. But however, if it is a small, then the flame front will be suffering the curvature effect, because of curve it is not really one dimensional also, right, and some strain will be experiencing, and the strain rate has to be looked at it, that is also an error. So, generally when it is a larger, like the strain effect will be reduced. So, you can really measure the burning velocities. And you can use a cylinder, you can use a spherical bump depending on that what is that. Generally cylinder is more preferred than the spherical because of fabrication problem, and also the strain rate in case of cylinder will be low. So, as I told, the combustible mixture is ignited at the center of spherical vessel or a constant volume or a cylindrical, right, and flame propagate toward the wall, and pressure temperature increases due to adiabatic compression, because the flame will be moving, it will be because of hot gas at the center, it will be expanding, right, density being lower. So, it will be compressing toward the wall when the flame front will be moving. And if the flame front radius is known, then you can find out basically how much the flame is moving. If I take this as a center, this is basically Rf, and I can track the Rf with respect to time, and then I will have to look at, because the rho b is at the center, this is rho b, and rho u will be after the flame front kind of thing. You can say if I am considering this as a flame, then this will be rho u of the mixtures. And keep in mind that this rho u evaluation is not that easy. Why? because it will be some heat will be transferred and it is radiation. This will be also not ambient temperature when you start the experiment, right. It will be attaining some values. So, therefore, this is evaluation is a very important point, and of course, what temperature you will be talking about, that also another thing. Rho b generally people consider to be the corresponding to adiabatic temperature, and rho u is the unbound, but it need not to unbound. So, therefore, this Vf dRf by dt you can get from the defining the Rf with respect to time, and you can measure that Vf, and rho b and rho u are to be evaluated to determine the laminar burning velocity. As I told that rho b density of gas mixture at burnt state, generally you can evaluate at T adiabatic here, and this is T u is supposed to be evaluated, but however, it need not to be T u, it may be little higher than the unburnt temperature. So, assumption what is being made here, that effect of flame front thickness and curvature are negligibly small, which is the assumption in this equation, right. And curvature effect is negligibly small in this case, and pressure at any instant is uniform throughout the vessel. That is again assumption being made. No heat loss including radiation, which is not real the case, but it should be, particularly when the flame front will be moving towards the wall, heat loss will be definitely there. But when the flame front in the middle of the this thing, then you can say okay, flame is far away, heat loss will be not that much, and then generally flame will be moving at certain velocity. So, therefore, it is a very fast process than the whatever heat loss could occur. And chemical equilibrium achieved behind the flame, which need not to be the case, because this is a very fast process, right. These are the assumptions being made for this. So, soap bubble, what is being done, basically this is the soap bubble, right. This is the fuel plus air mixture in a soap bubble. And if you look at his igniter, this is unburned mixtures, and at the time t when you ignite certain time, the flame will be moving in front and towards that, and then you will have to track this flame and look at it. So, this is you can assume it to be spherical flame front, and this is the, of course, the when flame will move, it may go little expand also. So, bubble surface, instantaneous flame surface. So, homogeneous fuel air mixture is confined in a soap bubble. On ignition at the center, spherical flame propagates, and pressure of burnt gas remains constant as the flame propagates. Assuming flame to be spherical and pressure remaining constant, mass flux you can say SL is equal to A rho u Vf into A, and this A is cancel it out. So, you will get basically SL is equal to Vf rho b by rho u, and Vf you can evaluate basically in the similar way. This is your Rf, and Vf is nothing but dRf by dt. You will track that values and then find out. So, this method cannot be used for dry mixtures, because when you are using soap bubble, there will be some kind of a water coming into picture, because you will be putting into that, and a flame front may not retain the spherical shape, and flame front won't be smooth for the fast flames, right, and heat loss to the electron and ambient environment also incur error, right. So, this is the thing, and with this we will stop over here. In the next lecture, we will be discussing about more methods how to evaluate the laminar burning velocity. Thank you very much.